I'm going to be presenting on my thesis, which is using machine learning techniques to try and predict well-being scores and to try and understand which of the covariates help us predict the score most accurately. So that kind of links to what Jacob was doing earlier, except his was strict causation, but this, I guess, is essentially correlation. However, sometimes when you look at correlation, you can get an indication of what may be causal. So I guess that would be the motivation behind doing this exercise. So my plan is to give a quick introduction in a bit more detail, talk about the data. The methods and the results will be the two main sections of the talk, where I'll spend most of my time. So I don't know what's most appropriate, and we can kind of decide as we go in balancing between people understanding how these methods work, the neural networks, decision trees, and then seeing what results actually came out. So I'll just try and see what people want me to do, and if you think you want me to move on to the results sooner or stay on the method, just say I'm happy to do either. Yeah, so the aim is, as I said, and my guess hypothesis before I started was that neural networks would most likely be the best and most accurate prediction of the well-being scores. And so the issue, however, comes that normally you can't interpret neural networks, and they're a black box. They just give you a prediction compared to a regression where you have coefficients, say. So one thing I looked into and I found is that there are ways to interpret neural networks, and that's one of the main points I want to highlight in the thesis. The results, the main message from the results is that they all do quite similarly in terms of accuracy. So the neural network isn't that much better than a logistic regression. However, I'm going to show you what I think is called a confusion matrix, where you can see that even though the accuracy score is similar, the results coming out of the neural network, to me at least, slightly make more sense. And all the models differ quite a lot in terms of what they say is important for prediction. Similarly, I think some of the interpretation for the models doesn't really make sense. The variables that come out, you look at and think something's going wrong here. But for the neural network and the random forest and the machine learning methods, the variables that come out do make sense, to me at least. In terms of the data, I don't know how many people have seen or used the Gallup US Daily Poll. So just for people who haven't seen it before, I compiled it into 10 years. Overall, once I did all this, put stuff together, got rid of variables where there weren't many observations, there were 106 different variables, which were numeric, say, how long is your commute to work, categories, one example is what is your job, and finally binary, are you married, are you employed, and had nearly 2.3 million observations. The score that is being predicted is the life satisfaction score. So asking people to rate their life between 0 and 10, where 0 is the worst life they can imagine, 10 is the best. And then the other 106 variables fall into these categories that I've put up. I did this myself, so these aren't official categories, but just groupings that I thought of using that make sense. In terms of missing data, I dealt with this in two main ways. One was if there wasn't a lot missing, just imputing the mean for the numerical variables. And for the categorical or binary, I created another variable to indicate if that was missing or not. So, perfect, I think. And then I've put a few of the questions up here that I'm just going to quickly skim through. I don't want to focus on it, but just so you know what is in the data set. You have the data, it makes sense. The community, so something, do you feel safe walking alone, are you proud of your community? These were somewhat more subjective. Medical, do you smoke? Have you ever been told that you have certain diseases such as cancer? These ones was quite tricky to decide which ones to put in or not, because some of them essentially proxy for your life satisfaction score. But things that I thought were interesting and kept in were something like, have you reached most of your goals, which is getting to a sense of achievement. Economic income, economic conditions in the country, home, marital status, job, employed, whether it's part-time, where you live, what state, physical characteristics, and political, religion. Yeah. So, I mean, does anyone have any questions on the data or what was in there? Okay, perfect. So I'll start talking about the methods then. So there are five methods I used: Rich Classification, Logistic Regression, which are very simple and are the methods that are normally used. Then the newer ones, machine learning, were decision tree, random forest, and neural network. For each of the methods, I calculated the accuracy score and then did the interpretation of which features or covariates were important. The Ridge classifier works by grouping, for the 11 different well-being scores 0 to 10, you create group, and for each one you have a prediction of the probability, and then you choose the one with the highest probability. And how it works is very simple, minimizing least squares regression. It's very similar to OLS. And then there's also a penalty on the size of the coefficients, which is called regularization. And that's used a lot to prevent overfitting. So when I did this, I once did it without any regularization to just see what a traditional econometric model that's normally used would get. And then also I found the optimal value of alpha and calculated the model using that.
So can I just ask you that?
Yeah.
So I'm a little confused. So this does it only for binary outcomes? So you're not predicting the score between 0
So
and well-being?
it's like a limited dependent variable model. So you have, if you have the score which is 0 to 10, I then treated that as 11 different groups.
Right, so you have 11 ridge regression.
Yeah, so that's what's going on behind the scenes. You'll have 11 of these, and then it chooses the one with the highest score. Before your output gets changed from -1 to 1, so say I'm 8, my well-being score, I will have a 1 for 8 and -1 for all the rest, like a binary. And then the regression would be run to predict my score. And the one that comes out as the highest would be my predicted score.
Sure, I was just trying to, because is there anything that ridge isn't required to be binary, is it? You could do the ridge regression on this sort of,
like a regression model.
It's just like elastic net would be some measure between ridge and lasso.
Yeah.
So you could. So I was wondering why you did it as.
So I wanted to try and keep, because the main model I was using to proxy for the traditional models was the logistic regression, which predicts you into a group. So I wanted to keep it that consistent across all the models, that they predict you into a group rather than predicting a continuous score, because then some models would predict a continuous score and other would put you in a group, and it would be harder to compare. So this is very basic and would never be used from what I've heard and seen. The advantage of a model like this is it's sometimes quicker to compute than a logistic regression. But the logistic regression is the main traditional model, as I mentioned. So again, you're minimizing the subjective function, where here you have the logistic loss. And again, there's a lasso loss put in at the start, which isn't normally used. And I do it once without the lasso and then again with the lasso. And it's similar to the ridge in that you predict a probability of you being in each of the 11 groups, and the group you fall into is the one with the highest probability. Yes?
So in the first case, I took that notation to mean, in this case, you take for the last term, that you take the absolute value?
Yeah, this is absolute. So
and in the first case, you took the squared value.
Yeah, so what this notation means, I'll write it up.
I just wonder why the square in the first case and the absolute value in the second case, or is this just a standard?
So this is a ridge loss on the coefficients, and here it's the modulus because I do the lasso loss. So they're different. The lasso has the advantage that it puts terms to 0, and it kind of has an inbuilt feature selection. So there's another version of this model which includes the ridge loss. So you have one term that's like the absolute value and another term that's the squared value, which is called elastic net. That's what Michael mentioned earlier. The reason I don't use that, to be very honest, is it sometimes doesn't converge and it takes a lot of computational power. So that's why I didn't use it, but that is another way to do the penalty. So those are the basic models. Onto the more more complex machine learning.
So I understand. So you could have essentially, when you do these 5 other methods, you're going to be able to compare them for each value of subjective well-being. Is that right?
Yeah.
So in some sense, you can work out what the best predictor is for score 8.
Yeah, and
a different one for 7.
Yeah.
And is there any way of aggregating that? I mean, that's the sort of downside of the approach, right? It's not easy to do a marginal value of, say, including score on unemployment.
Yeah.
Because there's a different score, there's a different effect of unemployment for score 1, 2, etc.
Yeah.
So you're just going to present results for each of them?
Yeah. So I present the results for all of them, and that is one thing I was interested to hear what people say, is that the main measure that's used is a accuracy measure, where you see what proportion of people were predicted correctly, but that's kind of gets to similar to what you were saying. That's not necessarily the best measure, because if you predict 7 for someone who's an 8, that's better than predicting 5. So we can see that visually on the confusion matrices that I'm going to put up, but in terms of the raw score of the model, it's not included. It doesn't take that into account. So I'm going to spend a bit longer speaking about how a decision tree actually chooses what to put in each of the nodes, because when I started, that was something I had no idea how that works. But if people feel we should move on, just stop me and we can. So one thing I've done is I've actually printed out and made a simple version of a simple decision tree on this data. So there's one, I don't think there's one for everyone, but maybe one between 2. And the two, one is the decision tree, and the other one is a key for the variables in the decision tree. And a few terms, just so you know what I'm referring to. The first node is called the root node, and then these orange ones are called decision nodes, and that's where you have something such as, is my income less than this number? Or for a binary, are you male or are you female? And it splits the data further until you come to these green ones that go no further, and that's why they're called a terminal node. And then, so this a subtree is quite self-explanatory. It's just a section of the decision tree. And one thing that's not mentioned here, but is really important, the issue with decision trees is that they often overfit the data. So you could imagine that if you kept going further and further, you could have one individual in each of these final boxes and predict the data perfectly. But then that wouldn't do well outside your training data. So there's a process that's quite important called pruning, where you go back and get rid of some of these decision nodes because they're not actually doing much, and that's how you get a smaller tree, along with stuff such as specifying how deep it can go. So on the one you guys have, I specified 3 levels because any more and you wouldn't really be able to read it.
So on the pruning, though, it seems very important, your decision to go for 3 levels rather than say 4 or 2. Yeah. On what basis?
So the way I did it is by using a grid search of specifying different values and seeing which one does best. And with a lot of these techniques, it's a lot about doing an effective grid search or trial and error in terms of the parameters to see what does best with your model. So yeah.
So what am I supposed to be inferring from? It's like a string of numbers and letters to me.
I was gonna come on to that. Yeah, I'm gonna first explain how that gets made theoretically, and then discuss the actual one. So what happens at each, going from your top node, what's happening is that the computer is trying to split the nodes such that you get as pure a sample in the boxes or the child nodes that are created. And it does this using an algorithm which, to explain intuitively, is quite simple. So you start at your first node and you take all my 106 variables, and for each one of them you see what would be the optimal split point to have as pure child nodes created as possible. And I'm going to come on to how we measure purity. I'll come on to that. So you do that for each of the predictors, and then from all of those optimal ones, you choose the best one to get what would be amongst all your variables, and taking the optimal point for each of those, the single best splitting point, and then you split by that. And then you keep doing that iteratively until you reach some reason to stop, which would either be you've got into your maximum depth, or you have a pure node so it can't split any further. Yeah, Casper, you...
It seems like you could. It seems like you're not forced to do a single split at a single node. Is there some reason why you force it to be the case that you split once on one predictor? Or is there some...
Yeah, I know. Yeah, so to be honest, it's just what seems to happen in the algorithms. But I don't see a reason you couldn't change that. Yeah. It's just they're all made to split on one node. And I wouldn't be surprised if there are some out there that can use multiple nodes, but it's not what you tend to see.
Isn't it just computational?
Yeah,
It's easier to just each time look at one split, the best split, and you move to the next.
Right.
You can always replicate a double split.
So that's what I was wondering.
One, but I think it's just computationally easier. I'm sure someone's got a big computer and has done multiple splits, but I bet your laptop would struggle.
Yeah, well, yeah, on my laptop, yeah. Yeah. Well, yeah, so if you think about it, say you have your commute to work, how long is it? If you're just looking for a binary split, that's quite easy because you can go through each value. But if you're looking for a 3-way split, you could, I don't know how many, but you could have so many more combinations, because you could have that first split anywhere and then the next 2 anywhere, and yeah, it would just be too computational. So this is quite mathsy. I put it in case people were interested, but I'm going to try and just explain it intuitively. So, and this is getting to how we measure the purity. And at any node, let Q represent the data at a node. What this line is saying that you have some TM, which is your threshold. So if we say there's a binary variable, male or female, where male is 0, female is 1, if TM is 0, then less than or equal to 0, you go to the left, and if you're male, and if it's 1, so you're female, you go to the right. So that's, say the data has been split into 2 nodes. And then the impurity comes by taking the weighted average of the impurity of these 2 nodes that are created by a loss function that I'm just about to discuss. But does everyone understand the idea that when you split a node, how you see how that split does is by calculating the weighted purity of the nodes that are created? You don't, so I'll maybe draw on Michael. So say, what I'm trying to say is if you go from there to there, and I'm just putting this arbitrarily right now, but say the impurity score is here is 10 and here is 20, and there are 200 people here and 500 here, your overall score would be a weighted average of these two, so 2/7 times 10 plus 5/7 times 20. Yeah, so that's, and you're trying to minimize that. When I said you're trying to minimize this measure of purity, that's the measure. And then how you get that 10 and 20 is this function h, and there are different choices for what you can do. One is, the 2 main ones used are called Gini and entropy. And what these P's represent are the probability of being in a group. So say there are 10 groups, the score for one of the nodes would be this calculated for each of the 10 groups, and higher scores represent more disorder, and lower scores represent a purer node where everything has a similar value. Are there any questions on that? Because I know this is quite mathematical, but any?
So I guess is another way of saying this is just like saying you want to have a split that's pretty decisive.
Yeah.
Right? So 50-50 is about the worst split you can do. If the probabilities are 50-50, that's like the worst you can do, because it's just a coin toss as to whether you're right or wrong.
Yeah.
Whereas like 90-10, you're getting actually better.
Yeah, that's exactly, yeah. So what these measures try to do is, if you have a 50-50, that score will be high. Yeah. But if you have a 90-10, it will be lower and represent more purity.
So you're trying to minimize a weighted sum of h.
Yeah. So you'll have an h for each of the nodes, and you want to minimize the weighted sum. Yeah.
Right.
And h comes from calculating this figure for each of the classes or groups within it. But I mean, what Michael said gets to the point very well. It's about being as decisive as possible. So you don't need to worry or focus too much on the maths if you're not interested or don't want to. The next method which I use is random forests, but they fall under a wider category, and I think this is really interesting. So here what you try to do is you try to aggregate a load of different decision trees or machine learning methods and get an average across, say, 100 of them or 500 of them. And there are 2 types. One is you build 500 independent decision trees, take an average of the score. The other, which is really interesting, I don't present it here, but would be an alternative method to do, is where you build your next tree, keeping in mind the trees you've already created, and trying to minimize, and trying to do as well as possible. So to give you an idea of how this may work is, that one algorithm, you build your first tree, and you calculate which individuals were predicted correctly, and which were predicted incorrectly. And then when you build your next tree, you give more weight to the people who were predicted incorrectly, so that you're trying to create a tree that will understand what you couldn't understand the first time round. And those are called boosting methods. But I'm going to focus on random forests, which is what I've done here. And how a random forest works is it tries to introduce stochasticity into the process from 2 dimensions. One, every time you compute a tree, you don't necessarily use the whole data set. You use a random sample of it, the size of which is a parameter that you can adjust. The second way you introduce this randomness comes from only considering a subset of the features whenever you make a split. So earlier we said you'd go through for the decision tree every single feature that there is. But what's done here is you say there are 100 features, you may only consider 15 of them at each split. And which ones you consider is done randomly. The reason for doing this is the idea is that decision trees often overfit. But if you create decision trees which are different randomly and then take their average, the errors are likely to cancel each other out. And then in the end, you'll get a much better prediction score. And I do find that here, that it does work and it does do better. So the neural network is the final one I want to discuss. This can be a quite complicated discussion, or it can just be very simple. So do people have any preference how much depth I go into on it? Is anyone very interested to learn how exactly okay, yes, so I think the best way to do is with an example. And so sorry.
Do you want a tissue?
I'll try this one. Yeah. I think it's fine. It doesn't really. I'll just draw a line there. So just say, so yeah, this. If you can everyone see clearly these 6 circles, 5, 4, 3. So these would be your nodes that form your neural network. And you have your input nodes, which is all your covariates. So to give you an idea, I've labeled it age, income, employed, married, and a score for each of those. And then you have the output layer here. So I've done this theoretically as a problem where there are only 3 groups, just to be able to draw it. And each one of these would be a probability for each of the groups. And you choose the one with the highest probability as your prediction. And then in the middle, you have all these hidden layers, which is how you get from the input to this probability. And what would happen is at each stage, you'd have these, so each node in any layer is a weighted average of the nodes in the previous layer, put through some nonlinear function. So to write that up, if your weights are omega, and your values here are x, and then you have like a constant term, and then you put that through a function, and that gives you the score that goes into here. And this function, there are different ones you can choose, but it may be, say, to get a score between 0 and 1, so a logistic function. And that happens at every level. So it would be similar here. And what this does is it allows you to introduce a lot of non-linearities into the data by having that nonlinear function to transform it. And it comes out to the final layer where you have your probabilities.
Actually, is the nonlinear function,
Yeah.
is the functional form of it the same, with just the coefficients in each node and in each level, or is it the same?
So the functional form is the same throughout. What's differing to get this one compared to this one is the weights that go on to there. And so what that neural network tries to do using that structure is to minimize this loss function. I'm not going to discuss it, but it's basically a loss function. You can think about it as least squares, just a method of trying to see how good your predictions are. And that's what you want to minimize at the end. So that's the structure and the aim. I can now talk about, which I think is very interesting, but is quite complex, how you actually choose these numbers, the weights that go into the neural network. Should I? Yeah. So the best way to do this is to actually put some numbers on. So say these are your three groups, 1, 2, and 3. And this person belongs in group 2. So this should be 1. This should be 1. That should be 0. That should be 0. That's the true state. Yeah. So that's the true state. And I'm just going to randomly pick this at one of the iterations of training the model. Let's say that what's actually coming out is 0.4, 0.2 there, 0.1 here, and 0.7 here. So your loss function would be telling you that this needs to go up, this needs to go down, but it's nearly there, and this needs to go down. So these two are the ones you really need to change. So I actually should have drawn these arrows coming to here now, but yeah. Sorry, this is going to be quite messy.
Surprised with all the alcohol on our fingers, it doesn't just wipe off.
Yeah.
Have a tissue and
Yeah. Sorry, guys. Thank you.
Turns out though this is alcohol free.
Oh, is it?
Yeah.
Oh, it does do a bit though.
Try it on a tissue.
Yeah, it does. Thank you, Michael. Yeah, that's fair enough. Thanks.
High school chemistry finding paper.
Yeah, okay, where's mine? So now imagine, I'm going to put the scores in here. Just and so I've got, in case you can't read it, I've got 6, 0.001, minus 1, 0.4, 0.4, 0.8, 0.9, and 0.1. So, and these scores are coming from, essentially how we get these are from the weighted average of them, and this comes from the weighted average of the one before. Now what you can see straight away is if you want to increase this 0.1, there are two main ways you can do that. You either increase the weighting coming from a node with a high score, or you increase the score on the node. So what the algorithm would try to do here is it would see that the 0.8 and 0.9 are the big ones, but they have a negative and a pretty much 0 weighting. So it would increase here and increase here. And then it would also see that this 6 is really high, but that's only 0.4. So it would want to increase the value that you have on this node. And then knowing you want to increase that node, you do the same process looking at the weightings and the nodes on the level before. And you keep going back, doing it for each node in each layer. So as you can see, it's quite computationally extensive. And that's called backpropagation. And that's the intuition behind how it does those weights. It will go through the whole network, do it for each observation, and then repeat that a few hundred times or less, depending on what you specify. So now that we've discussed all the methods, unless anyone has any questions, I'll go on to the actual results that came out.
So just to be clear, so in your actual estimation, you have like 100 first layer nodes and 11 at the end.
Yes, yeah. And in terms of the middle layer, so I spoke quite a lot with people who actually do neural networks the whole time, and they said you have to just search and look for what works for your data in terms of how you specify the layers in the middle and how many nodes to have for each layer. That's, it's like grid search or something along those lines.
Is there any intuition to be had about both the number of layers and the number of, I guess the term is neurons?
Yeah.
Within a layer?
So there are two things. I think the first thing, which isn't so much intuition, but kind of always is the case, is if you have too few, it can't learn the data, and if you have too many, it's probably going to overfit. So that's a general rule. One way people often look at it, but I'm not sure if this works in practice, is that the computer is trying to, say you have your scores, the level before are the final determinants. So it could be that one node represents your job-related aspects, another node represents health-related aspects, another one is community-related aspects, and then the node before is like even wider, like more specific, all the way back to when you just have one aspect. So that's one way you could think about it, but you can't really, it's hard to say, or at least from what I've done, you can't really specify that when you're training the neural network. But in an ideal world, I guess that's what it's trying to do. And what it's saying is, say here is job related, the nodes that will have high weightings are the inputs that are related to your job, while an input such as your age may be 0 for that node, but be high for the node that represents your physical features.
So just a general observation, because I'm so unfamiliar with machine learning AI type techniques, but it strikes me the extent to which AI, machine learning, still requires a lot of, the machines still require a lot of training.
Yeah.
Whether it's training here into deciding how many nodes, how long, or the pruning in the forest or the decision trees. There's a lot of still openness for human arbitrariness to some extent, searching, false positives, the fitting. AI does require, I mean, what's your sense like on the basis, is there, because I was kind of hoping or thinking that these kind of neural networks in a way tell us what the optimal level of those are to get to the optimal outcome. It still seems that we have to tell the machine, train it.
Well, you could do.
I'm completely naive on this one, but it feels like there's still a lot of human involvement in trying to set this right.
So yes, unless you had a extremely powerful computer that could do a grid search on every possible combination and tell you which one does best.
That doesn't exist. Would it be too computational intensive?
It's like, I mean, so there's no limit on what the middle layers could be. It's like you could have anything in the middle.
The only limitation would be the number of variables.
No, you can have more middle layers than even variables you have. It will do badly. It won't predict well. But theoretically, there's no limit on what's going on here. It could be any shape or size. And also it's not just that's one parameter you're putting in. This neural network has about 15 different parameters you can specify. So it's not feasible to do a complete grid search. And I did a grid search focusing on the most important parameters, which gives you an indication.
We've already crashed enough fields supercomputer.
Yeah, a few times. Yeah. So I've got 15 minutes. Okay. So these are the scores that come out by model in terms of accuracy, predicting correctly.
Accuracy here, again, pardon me, are we reading this a bit like a Bayesian invariant grid, like the lowest is best or the highest is best?
The highest is best. So the neural network does the best.
So that means it gets the right life satisfaction score
The most frequently.
35% of
Yeah.
the time. Right.
And so the Ridge gets 33%, similar with the Logistic. The decision tree does the worst, which isn't too surprising because it's the advantage of decision tree is that you can interpret it, which reminds me I forgot to actually speak about the decision trees I gave out. So I'll quickly just spend 1 minute. Thanks, Jacob. So yeah, if everyone just has a quick look, all I want to highlight with this is how easy it is to look at it and understand what's going on. So you just follow from the top. If you take a certain individual, you follow the yes, no down to the bottom, and then you see that there's a class at the bottom which tells you whether they fall into 1, 5, 7, 8, or whatever. And what's nice is, obviously, whatever comes at the top is the most important because that's doing the first split. And the ones that come lower down are less important. And you can see that the first one is, I think I've written it down on the key. Yeah, it's are you satisfied with your standard of living? And if you say you're not to that, if you say you're not satisfied, you can only go up to 5 in terms of the prediction because all 4 of the boxes on the right hand side are 5, 1, 5, 1. So it's saying straight away from that one question that gives that inference for the predictions. We can speak about that more later or afterwards, just so we have, sorry, Jasper.
Did you train these models on the full sample, or did you train it on some subset of the sample and then applied it to?
I did 70% training and then 30% testing, which is where the scores come from. So yeah, the decision tree does the worst, but what I think is very good about it is the way you can just look at it there and understand straight away what's going on.
So I read these as really small differences in accuracy. Is that right?
Yeah, that to me, yeah, I was thinking if there's any way to significance test them or not, and I couldn't find anything, but they're small differences, which was not what I was initially expecting. I thought the neural network would do way better, and I think there are two reasons that can be. One, maybe the data or the relationship isn't too nonlinear, which I don't think that's what's going on. I think it is probably likely to be nonlinear. The other thing is with the data there that's subjective, there are going to be a lot of contradictions. So people with exactly the same features that give very different scores. And with an iterative process like that, I think potentially that means the neural network can't really take advantage and do extremely well. Because often you should be getting your training data set accuracy up to 90%. And this one wasn't going above 40%. I think just because the data is so contradictory. And the final thing that could be going on and is probably likely is this is like when I do say regularized, I found the optimal parameters because there was only one. So that's as good as the Rich classification could ever do. This is my best attempt at a neural network. And maybe if I had a full grid search, as we mentioned, had more time, this could go further up. But I mean, I did spend a lot of time on it. I couldn't get it much further up. Yeah.
You mentioned you trained on 70% and then did half a sample on 30. Is there any difference if you train it? So because here the heuristic score are very similar. I'm wondering maybe is some of these techniques better when trained on 50%, and is there any major difference so that with more parsimonious information?
That's interesting. I haven't thought about it like that at all, to be honest, until now. No, I think I see your point. I've always seen it as the more training information, the better, has been my intuition. and I think is the general intuition. But I'd look into it. I can get back to you because I wonder if maybe there's a point where you have too much information. But that's yeah.
Because for sure the accuracy is going to improve, but maybe not at the same rate.
Yeah.
So this is.
Yeah. So neural networks. These methods require a lot more observations in general. So the neural network, if you put the training sample size down to say 25%, the neural network would do really badly. And that's what allowed me to use the neural network in this situation, was that I had 2.4 million observations. Yes.
I think Alberto makes a very important point. So if you're framing your thesis as which of these machine learning methods is the best at predicting well-being scores, most people, sadly, don't have access to the Gallup daily poll. They have access to much, much smaller data sets.
Yeah.
Right? And so it would be very useful to know which method yields the best prediction at a given sample size.
Yeah. That would be.
And so if you could like show, okay, with an n of a meager 1,000, my rich regression dominates them all, but as soon as we get to 20,000, the neural net wins every time.
Yeah.
That would be guiding to many researchers, I think.
Yeah, that's right.
So that's one very good point that would make it very pragmatic, I think, for people to use. And when a shift happens from ordinary OLS and logistics onto machine learning, the other note here is we shouldn't minimize these differences either. So the fact that the neural network provides enough and sufficient data, say 4 or 5% better than the traditional logistic regression, that's a big deal if you think about it in practical policy terms. I remember when Sid came to me with the first impressions of these relatively meager results. I said, well, if you go to a trading floor in some kind of bank and you tell them you can predict the stock market 5% better than what they previously could with prior methods, they'd be jumping around. And so maybe we should be doing the same here. And so it's fantastic to know that new methods on big data can do better.
Yeah. And when I show you, so like the next slide, I'll start showing the matrices, and I think there you can see that the ridge does well, but in a way that's not very satisfactory. So, and to show you,
just on that note, so I mean, the really striking thing about how accurate these are is they're all so much better than randomness, right? So that's less than 10%. So
not quite. Randomness, if you don't include the frequency by which groups are chosen, but the US is a relatively, on this scale, does quite well and has 25% of people, I think, or just less than 25. Yeah, 25% choosing 8 in the data set.
Okay, so the thing I was going to suggest, because I think the standard errors would be very nice to know, right? You can repeat this, or you do repeat it for many training samples, right? So you actually have a distribution of these accuracy scores, right? So I'm sure there's some configuration of, even if we stuck with the 70-30, there's some configuration of that where you get 50% and then other times you get 20%.
Yeah.
Because the second point is not just I'm more accurate and regularly at 35 as opposed to, maybe one of them you get 35 sometimes, but you get 2 sometimes. And then you'd be really worried that if you got, again, going back to other researchers, if they pick up a data set and they don't have as much data, and it just happens to be they use all the data, and it turns out they don't know it, but they could be using a method that's incredibly volatile. So they might be having a great fit, they might be having a terrible fit out of sample, but they'll never know. And you can actually test that if you just look at these.
Yeah, like
they might be very similar. Yeah. And I don't want you to break the Nuffield computer again, but it seems like something you could do.
Yeah, no, definitely, and like almost create like bootstrap standard errors.
It's bootstrap distribution, but they're not even bootstrap. You have them. That's how you get these average accuracies because you've taken.
Yeah. Yeah. No. I should have done that. So. Yeah, onto the Rich Classifier. This is your predicted label on the X, and the Y is your true label, and it's standardized such that each row adds up to 1. So this 0.48 means that 48% of people who were actually 1 were also predicted 1. While this is 23% of people who were actually 1 were predicted as 8. So when I saw this, what I made of it was it's doing well at predicting the worst, the category 1, and then it's essentially saying 8 most of the time. And it never predicts 9 or 6, which to me it gets to a decent score doing that, but yeah, apart from 8, it's predicting 4% of the time.
It beautifully illustrates what Michael so nicely put just now, in the sense that, I mean, you can be relatively good in predicting and be clever if you choose 8 all the time.
Yeah.
You can be so widely off. And there's a lot of mistake or disutility from being so widely off, whereas your neural network will be much less often wide off from where the actual thing is. So that's even though in terms of the statistics and predictability, the standard deviations here. The standard errors.
That, I think, adds to it. And you explained in the beginning why you chose to just predict each label.
Mm-hmm.
But it seems that, are we really interested in getting the 8 right? Or are we interested in getting close to the 8? Right? So we'd be much more happy for my model to predict a 7 rather than a 1 when the true score is an 8.
Yeah.
And so I wonder whether there's not quite a lot to be gained in treating the scores as at least ordered.
Yeah.
And having the penalty for these models taking the ordering of the scores into account.
Yeah.
But you don't need to force it to be cardinal, but at least have the penalty respect the ordering.
Yeah, that,
Seems to
yeah.
be important.
Yeah, no, I agree with you, and that's, yeah, so I was thinking, like, what could such a score be? That's something I was looking into, and maybe the next step. Because, yeah, I don't think it's, even when I do the hyperparameterization, it's based on the accuracy score. But maybe it should be based on, say, your score plus 1 either side, maybe. So yeah, that's a good point.
So just very quick one. So now the focus has been on life satisfaction, or the Cantor ladder, as an evaluative measure of well-being. As we all know, there's also more emotional measures of well-being, like positive emotions or the absence of negative emotions, and even purpose and meaning, these kind of things. So all of this has been trained or has been run on Cantor ladder only.
Yeah.
The reason I'm asking is I'm kind of curious to see whether the predictiveness goes up or down if we take different types of measures of well-being.
Yeah.
My hypothesis here is that the life satisfaction is probably the more stable one and easier to predict as compared to emotional well-being, which is, as we know, much more seasonal, moves around.
Yeah. Yeah, so that's, yeah, I think that would be a very interesting exercise, and it is like the one I would, like, the next step in the process. I just haven't really had the time to get to it yet. But yeah, I think that's the next thing to do with this, is look at some other Y variable. For the Rich Classifier and the Logistic Regression, I did a quick feature importance, or based on taking the coefficient score, coefficient for each feature for the 7 different regressions. One thing I forgot to mention at the start is there's so few observations below 5 that we group them into 1. So this group overall is 8% of the data, so it didn't really make sense to keep it as separate. The main point here is if you look at this feature importance, it doesn't really make sense, because this is the same variable, which was a binary, are you in the workforce, yes or no? But I made it into 3 binary variables so I could deal with missing values. And both of them come out near the top, despite the fact that there weren't many missing values in this case, so these pretty much contain the same information. So I kind of took this to, like, going with that matrix, took it as the ridge predicts well, but doesn't really get it in a useful fashion. The logistic, we'll skip that. The logistic is similar to the ridge, similar idea. And again, when I did the feature importance, I just got that the years are really important, which I would expect some year variables to be in there, because the years kind of proxy for what's missing, because some questions aren't asked in different years, but this, again, didn't make sense to me. And then getting onto the decision tree, even though the score is worse, it starts to do better in terms of the overall shape of the matrix. I don't really have time to go into detail and point to the boxes that show it, but you can kind of, we speak about it later if people want. And in terms of the feature importance, it now, to me, the stuff that comes out is interesting. So a lot, it largely focuses on income, standard of living, money to meet your basic needs, such as food, and then a measure of health. But the large focus seems to be standard of living, income, money to meet needs. And with the random forest, again, similar to decision tree, getting there a bit nicer picture, but remember this does well on the accuracy score also. You notice, compared to when I said the 4% in 10 for rage, it's gone up to 15. And so the feature importance here, even though this model is sometimes pointed to as a good one to interpret, the issue is that it's biased towards things that are continuous. So something like height, weight are coming up high, and BMI, because they're continuous scores. So the feature importance here, even though the model predicts well, isn't that helpful. And then finally, the neural network, what you see here that I want to point out, does way better on the 10. And when I compare them, if you look at the diagonal, so that's groups predicted correctly, the neural network does better than all the previous ones for every group apart from 8, where it does worse than all the previous ones. And the reason is the previous ones are massively over-predicting 8, while the neural network takes 8 down but does way better everywhere else. And if you consider the fact that a lot of the loss in score compared to previous models is coming from 8 being worse, the neural network does even better than the score actually suggests. And just finishing off, these are feature importance. So you do have 2 of the years come up, which is slightly disappointing, but largely the ones that are near the top are similar to the decision tree, make sense, standard of living, money, and it shows that this method to interpret neural networks is providing results that, at least intuitively, are what we'd expect and should be looked into more, rather than just saying neural networks are a black box.
It seems
but
like it's the best of all
yeah.
of the methods that we've just seen.
Yeah.
So
But that's
sorry.
Maybe a quick question. So I actually personally don't buy that we can learn much from looking at the features, the feature importance here, because all the models differ so much. So it's really not that useful for causal inference, in my opinion.
Yes.
Maybe interesting, but not that useful.
Yeah.
So why would we want to forecast happiness in the Gallup poll? Like, what's the actual, substantial reason why, or substantive reason we would want to do that?
So one reason could be, if you don't have the data on people's well-being, you could, using their other information, try and understand that. It could be useful for scoring or for having a current understanding of well-being in different regions. The second is, even though I accept, kind of going back to what you said earlier, you can't buy anything causally because this isn't causal. So I completely agree with that, but I think it gives an indication as to where you may look to get causal variables. So I think you're right that it's not causal at all in any shape or fashion, but it's a starting point to get towards that, is my view.
Not in the absence of actual exogenous shocks or being able to have some kind of RCT within these data, because this is just observational data, probably gets closer to pointing in direction of causality than your typical regression does.
Okay, so just one thing. So the Gallup data set in 2008 does not have WP16, which is slide satisfaction, right?
Yeah.
But they do predict it, which is what you're trying to do.
Yeah.
So one thing I just thought is that you could take a model, train it on 2009 and onwards, and then try to see if you can match what Gallup themselves did. Because if you don't match it, you know that they know something you don't know. And if you match it or better, then you know you've probably done the best, because I guess they spent some money on it. Because they're not going to sell a predicted value that's useful. So I think that's really like the ultimate test.
Yeah.
Of all of that stuff.
Yeah, that would, I was, because I remember we discussed that, so I was going to look into it. The reason I hadn't done it already is I think I'd have to tailor the initial model a bit, because the 2008 data would have different variables to all the other years. So I'd have to almost do the whole exercise from the point of view of that end goal, if you see what I mean.
But you could do it on a subset, and I mean,
Yeah.
they must have done it some way. So.
Yeah, yeah.
That's-
But yeah, that I will.
Because
Yeah.
it was just an initial fun idea to see how good we could do, but I think now it's actually serious because it's a test.
Yeah.
So from what you're doing. So I think if you're not going to do it, I'm going to do it.
No, I'll do it. We can, we can do it together.
On that note, see Michael, thanks very much, Sid.